Just 30 years ago, this was the one planetary system we knew orbiting a normal star. This is, of course, our own planetary system. And if I tasked each one of you to design your own solar system from scratch, this might not be what you would come up with. You might be very egalitarian and have all the planets have the same mass and radius, or you might be very hierarchical and have the most massive, largest planet living very close to the star, and then the planets get smaller and less massive as you get further away. But that's not what our solar system looks like. Our solar system has 4 glorified balls of rock sitting in the very interior parts of the planetary system. Smack dab in the middle is the largest planet, made up of mostly hydrogen and helium. And then as you go ever further away from the sun, you get planets that are gas giants and ice giants living further and further away. Now, given about several hundred years of time to try to contemplate why our planetary system looks like this, you might not be surprised that we came up with some really good theories that predicted its properties. And these theories also predicted that other planetary systems should look more or less like our own. We could not have been more wrong. In 1995, just a few months after I started graduate school at Ohio State, a planetary companion was found around the normal sun-like star 51 Peg. And like Jupiter and Saturn, 51 Peg b is a gas giant planet, but unlike Jupiter and Saturn, it's not located in the outskirts of its planetary system. It is huddled up right up against its parent star. Its orbit is so small that its year is only 4 days. Now, the discovery of 51 Peg was a catalyst for discovering additional new planets and for astronomers to develop new methods of finding planets and hone those methods to find ever and ever smaller planets. And so our tally of exoplanets grew slowly over the intervening years until 2009, when NASA launched the Kepler Space Telescope. Kepler Space Telescope was a relatively simple machine designed to monitor the brightnesses of 100,000 stars over the course of 4 years and look for periodic dimmings of those stars as their planets pass in front. And Kepler was, by all means, extremely successful, wildly successful. Kepler found over 3,000 planets of all shapes and sizes and really brought the study of exoplanets into the statistical age. We now know of over 5,000 exoplanets orbiting other stars. And these exoplanets come in a bewildering array of sizes, masses, temperatures, atmospheres, environments, and so forth. Truly all very strange new worlds. And yet, we still don't know how common solar systems like our own are. We don't know how often nature chooses to make solar systems with architectures like ours. And that's because these methods that have been developed, say the radial velocity method, the transit method, the astrometry method, and the direct imaging method, are not sensitive to planets like those in our solar system. There's only one method that's really sensitive to planets that are analogs of those in our solar system, and that's microlensing. And that's where I come in. It's also where Albert Einstein comes in. And I know that sounds a little weird, so I'll have to explain that to you. I grew up in a small town in rural Illinois with a population of about 4,000 people. And that was hard enough, but I also happened to be gay, autistic, and a big nerd. So life was pretty challenging for me, and I was pretty clueless. But one thing I did know for sure was that I wanted to be an astronomer. And I carried that drive all the way to graduate school at The Ohio State University, where I met my advisor, my thesis advisor, Andy Gould. And Andy Gould told me about this new method of finding exoplanets that was completely like unlike all the other methods, and was in particular sensitive to analogs of planets in our solar system. This method was based on an idea that Einstein published in 1936, where he described the effect of a planet passing in front or a star passing in front of a background star. Although famously he said that this phenomenon would never be observed. one of the few times that he was actually wrong. The basic idea is pretty simple. If you stare at a star long enough, then eventually some other body, a star or a planet, is going to pass in front of your line of sight to the background star. The gravity of that body is going to bend and brighten the light from the background star such that you get a transient increase in the brightness of this background star. Now, if this foreground star happens to have a planet orbiting it, then you'll get a light curve that looks like this. You get an overall smooth, symmetric brightening and fainting and dimming, but then you can see those two sharp spikes. Those are the two sharp spikes are the signatures of a planet orbiting the lens. Now, when Andy presented this idea to me, it was nothing more than a nugget of an idea. But he and I and other people worked over the intervening years to develop into a practical method of finding exoplanets. And we were rewarded in 2003 with the first discovery of a planet with microlensing. And this is a Jupiter-sized planet located in the outskirts of its parent system. Then in 2008, I led a team of 60 astronomers to discover a scaled-down version of our solar system. So this is the first multi-planet system discovered by microlensing. It has 2 planets with masses and separations similar to that of Jupiter and Saturn. And this put microlensing on the map. Now, what happens next is even more interesting. You might wonder, how does NASA decide what kind of space missions it builds? These are billion-dollar missions, after all. How does it decide what missions to build? You might think that it's a couple of old white dudes living in the pinnacles of their ivory towers at places like Harvard, Princeton, Yale. You couldn't be more wrong. At the end of every decade since the 1960s, more or less, astronomers all over the US have gotten together and decided what they want to do for the next 10 years. These so-called decadal surveys are now the coin of the realm. And in fact, NASA and NSF are congressionally mandated to follow the recommendations of these surveys. And each survey typically picks one large space mission as its main priority. So back in 1972, that same space mission was Hubble, and then Chandra, Spitzer, and then in 2000, the James Webb Space Telescope, which I'm sure you've all heard of. It launched in Christmas of 2021 and is bringing back some of the most spectacular images of the universe we've ever seen. The number one priority of the 2010 decadal survey was a mission called the Wide Field Infrared Survey Mission, or also called ROMAN. Now, what WFIRST had 3 science goals. One, it was going to study the nature of dark energy and dark matter and how it affects the evolution of the universe. Second, it was going to study our galaxy and nearby galaxies to understand their constituents, including the gas and the dust. And third, it was going to do a survey of exoplanets that would be complementary to Kepler using the technique of gravitational microlensing. Now, this was quite a shock, considering at the time there were only a handful of people in the United States working on microlensing. So basically, we were given the task of making sure that this multi-billion-dollar mission was successful. No pressure. And to say WFIRST was popular would not be correct. It was immensely unpopular at the beginning. Astronomers thought it was a kind of Frankenstein mission with a relatively small mirror, much smaller than that of JWST, and only did a few a small amount of science. But then after much advertising and lobbying, WFIRST was gifted a larger aperture telescope, and the astronomy community started to warm up to it. And then in May 2020, just after the start of the pandemic, WFIRST was renamed the Nancy Grace Roman Space Telescope. And that's after Nancy Grace Roman, the first chief astronomer in NASA, and often called the mother of Hubble for her instrumental role in getting Hubble developed and launched. So now we are less than 4 years from launch, and teams of thousands of engineers are working to polish mirrors, assemble telescope structures, build filter wheels, and put on antennas to take the data from its position in space down to the Earth where we can analyze it. So what is WFIRST? WFIRST is a telescope with a mirror roughly the size of Hubble, but it has a wide-angle camera lens such that its field of view is about 100 times that of Hubble or JWST, and it has a mapping speed that's 1,000 times greater than either of those missions. So that means that Roman can map large areas of the sky very quickly to, for example, detect galaxies and measure their structure. Or it can monitor smaller areas of the sky repeatedly to look for variations of brightnesses of stars. And it's that last capability that is instrumental to the microlensing survey. So over the course of about 400 days, over the 5-year prime mission of Roman, it's going to look at a field something like this towards the galactic center, the center of our galaxy. And it's going to monitor the brightnesses of those stars. Now, this may look like a lot of stars to you, but this is actually only a subset of the field. I can blow this up for you. You can see even more stars in this image. But then I can blow it up, zoom out again, and now you can see even more stars, tens of thousands of stars. And this is only about 0.1% of the entire survey area that Roman will be looking at for microlensing. It's an area that is roughly 16 times the size of the full moon. And so Roman will monitor the brightnesses of those stars, and it will look for these transient events called microlenses, and then it will look for little bumps and deviations on top of those events that are the signatures of planets. Now, what makes Roman extremely powerful is that it's very complementary to Kepler. So this shows Kepler's search area, which you can see is limited to roughly planets with orbits less than that of the Earth. And this shows the search area of WFIRST, Roman, which covers the rest of the solar system, and so therefore is very complementary to Kepler. So Roman will detect will monitor the brightnesses of hundreds of thousands of stars. It will detect tens of thousands of microlensing events. And it will detect thousands of planets, including planets with masses as low as twice the mass of the moon. It will find planets that are not bound to any star, free-floating planets with masses all the way down to that of Mars. It will find planets orbiting two stars like Tatooine. It will find planets orbiting dead stars like white dwarfs, neutron stars, and black holes. And it will even find giant moons orbiting giant planets like the moon around the Earth, or Ganymede and the Galilean moons around Jupiter. So together with Kepler and Roman, we will be sensitive to all planets with masses greater than that of the Earth and orbital periods from basically 0 days all the way out to infinity, because Roman is sensitive to free-floating planets. So together with Kepler and Roman, we will be able to find all of the planets. And what's more, we will finally be able to say how common our solar system is throughout the galaxy. Thank you.